Welcome to our free GMAT prep hour for April 25th, 2022. I'm Dmitry. I'm your host from San Diego. Today's focus is going to be on everyday math. And what I mean by that is the kind of math that you might do if you're a little weird like me, while you're going about your everyday life. We often think about the kind of math that we are forced to do, like, maybe calculating a tip or splitting a check or, figuring out how much to pay for things. And we could talk about some of that. And I'm curious if there are everyday examples that you've encountered. I'd love to hear any examples you've noticed. But a couple things I thought might be useful to think about would be rate problems that we deal with on a daily basis. This can be things like working out in the gym. It could be running on the street. It could be driving or commuting in any way. And it can also be earning money on the job. And if any of these examples that I'm giving don't seem particularly relevant to your life, I happen to love to run on the treadmills. I'm a weirdo in multiple ways. If you don't do that, we can still think about the rates and the ratios that are involved for a lot of other problems we're doing that might be relevant to our lives. We can talk about some temperature conversion, and I'm going to try to mix in the idea of weighted averages and tendencies through a lot of what we do. So depending on how you're feeling about what we're doing, we can work more or fewer examples of each type, but kind of want to just get you thinking about some ideas. So we'll start with a data sufficiency problem. Sounds like you guys might have the experience, those who are participating live, to jump right into this data sufficiency problem. If you're doing this at home, you might just want to check on the rules for data sufficiency before we get in here, but basically, which of these statements is sufficient to answer the question? One alone, two alone, both together, either one, or neither. So that's A, B, C, D, E. I'll launch a poll for those of you who are here. Give this question a try, and then we'll talk about it. Okay, let's talk about, so I'll put up a quick reminder for anyone who's watching who doesn't remember their data sufficiency answer choices or is still pretty new to this stuff. But got some answers in. Not leveling these today because I would just want to spin variations on it. So I would, this isn't an official question. And if it were, it might not be a super hard level, but there is some sneakiness to it that I want to talk about. And so it's more about the idea behind it than about whether you get this particular one right. So what we basically want to think about is, if I'm driving faster, and this is what I want to talk about in a few different cases, because this is going to affect stuff that you do all day, whether you're driving, running, walking, working, collecting items, whatever it is you're doing, getting votes, collecting likes on social media, whatever you're doing, when you're looking at the rate at which you do those things, it's looking at what the marginal increase is in terms of number versus percentage at different levels. So if we look at just knowing the distance, right, we could say, well, okay, if I know how far she's going, then that certainly should affect the amount of time she spends driving. And I would definitely need to know how far she's driving if I wanted to find out how long it actually takes her. And so even if I don't have the rate, I would say, oh, it seems like statement one is necessary. But in this case, they're not asking us how long she actually takes. They're not asking us anything directly about distance. They're asking us about the relationship between rate and time. And so by itself, I could say offhand, hey, I don't know anything about rate or time, and therefore this is insufficient. If I weren't sure, I could test some cases. I could say, what if she's going 40 miles per hour? Then she's going to go 40 miles in an hour. So what would happen if she upped her rate to 50 miles an hour? How long would it take her then? And those of you just joining us, welcome. Talking about the applications of our everyday lives to the GMAT and vice versa. Can we use the stuff we do throughout the day to make us better at the GMAT? Okay. So anyone got a thought about that? If I'm going 50 miles an hour, but I want to go 40 miles, how do I calculate that time? If I want, I could create a rate chart. Rate times time equals distance. And I'm going 50 miles per hour. I'm going 40 miles. If I divide those to get time, I'm going to get 40/50ths of an hour, which is 4/5. And I would have to do that times 60, gets me 48 minutes. One quick way to do fifths of an hour is that there's 5 12s in 60. So every time I go a fifth of an hour, I'm going 12 minutes. Okay. So if she were going 40 miles an hour, she'd shave off 12 minutes by going 50 miles an hour. So what happens if it turns out she's going faster? Well, we could look at what happens if she went up again from 50 miles an hour to 60 miles an hour. Okay. So I could do the same thing if I wanted. I could do, okay, what if she's going 40 miles at 60 miles an hour? So I do 40 over 60 equals 2/3 an hour. A third of an hour is 20 minutes. That's 40 minutes. So one thing that's really interesting about this is that the marginal gain as you go up faster starts to dip. Going up by 10 miles an hour saves you 12 minutes when you're going 40, but it only saves you 8 minutes when you're going when you're already going 50. As you get faster, it's going to go up more and more and more and more. As you get slower, it's going to the increases. Sorry, let me say that better. As you get faster, the increase in speed is going to yield a smaller and smaller decrease in time. As you get slower, the increase in speed of 10 is going to have a larger and larger decrease in the amount of time you spend. It's going to make a bigger difference. Think of an extreme case. What if she's driving 10 miles per hour? Then adding 10 is going to double her rate. It's going to halve her time. Or even further, what if she's driving 1 mile an hour? I don't know why she's commuting at 1 mile an hour, but okay. If she's going 1 mile an hour, then adding 10 would multiply her speed by 11. She would take 1/11 as long as she usually does. It would make a huge, 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 huge difference. On the flip side, if she were going at the speed of sound or something, then adding 10 would barely budge her time. So this one would be insufficient. And if you're used to doing our AD-BCE method, you'd say, okay, if statement one is insufficient, you're going to cross off AD. So now what we've seen, we've already tested 50 miles per hour with the distance, but I have to be careful. I don't want to get into statement carryover. I want to look at statement 2 on its own and say, in general, if you're going 50 miles per hour, if you go up to 60, do I know the percent that reduces your commute time? So what do we think? When I initially pulled this in, not everyone was here. So let me try pulling this again. So at this point, if you think statement 2 is sufficient, you'll give me a B. And if you don't, let me do that again. If you don't, you'll give me a C or an E. So if you think statement 2 is sufficient, give me a B. If you think I need to combine it with the distance, give me a C. If you think that even combined with the distance, I cannot find the answer, give me an E. I think you probably don't want to choose E because we just saw with the distance that we could find the exact difference in time. So I'll nudge you away from E there. Okay. So B is getting a lot of support. Yeah. So why? We could test it with different distances if we want to, but we've already taken some time on this, and I don't want to spend a lot of time on any one data sufficiency problem testing a lot of cases. So I'll test the cases that I need to, but I don't want to do that if I don't have to. So I could say, all right, well, I tried it with 50 miles an hour when she's going 40 miles because of stable 1, but what if she was going 80 miles or 100 miles or something like that? But I could use something else instead, which is the fraction setup of the change in her rate. So I could basically say, okay, if she goes 10 miles per hour faster, she's at 60, right? Okay. So could you agree that she is going 6/5 as fast as before? So, and pardon me if this is already pretty clear to you, but I just want to make sure because this is something that I talk to people a lot about, and a lot of times they're just like, "You're weird, you and your fractions." If I'm going 6/5 as fast as before, what happens to my time? When you go 6/5 as fast, you're going to take blah 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 as long. Well, your speed increases by 20%, but your time doesn't decrease by 20%, and it certainly doesn't increase, right? So what happens to your time? If you drive 6/5 as fast, you'll take what fraction is long? And try to think of it as a fraction. I think thinking of it in terms of percents is actually going to be misleading for a lot of folks. It's a reciprocal. It's 5/6. Yeah. And if that's not really intuitive for you, it can help to use integers first, right? If I go twice as fast, I take half as long. I don't think that's very controversial to anyone, right? If I make twice as much money as my brother does, then I'll take half as long to save up, $1,000 or whatever, right? If I run twice as fast, my mile time or whatever will be half. And similarly, if I go, 3 times as fast, I will take, 1/3 as long. So I can do the same thing with fractions though, because I can say, all right, if I go, 7/5 as fast, I will take 5/7 as long. It's the same idea. They're all just reciprocals. 1/2 is a reciprocal of 2, 1/3 is a reciprocal of 3, 5/7 is a reciprocal of 7/5, and 5/6 is a reciprocal of 6/5. And this gets to, I think, one of the most central areas of trouble for a lot of folks when they're taking the GMAT is that when they're dealing with, say, percent change or something like that, they treat these as identical. They say, oh, if I go 20% faster, I will take 20% less time. And that's actually just never true. That's never true. The percent up and percent down never match because we're dealing with reciprocal fractions, right? If they're identical, sure. If you're 100% of the weight that I am, then I'm 100% the weight you are, right? You're 0% heavier than me and I'm 0% lighter than you. But unless we're identical, those percents aren't gonna be identical. If I weigh 10% more than you do not weigh 10% less than I do. And that is one of the most important things you can know about percents. And so we can see this. She's running, or she's not running. She's driving 20% faster, but her time went down by 1/6, which is 16.666%, right? 16 repeating 6. And in general, if you think of 6/5 and 5/6 as like canceling each other out, right? Just like if you have an investment that goes up by 20%, and then the stock market does so awesome like it's doing right now, and it drops by 16.6%, you're back to flat. It doesn't, if it drops by 20%, you're actually below, right? So a lower decrease in percent will make up for a higher increase because the decrease is going to be out of a higher number. Okay. And unfortunately, it actually creates the same issue the other way. If you decrease first, then the increase is out of a lower number. So either way, if you increase and decrease by 10%, 20%, 50%, whatever it is, you always end up lower than you started if they're the same percent. A lower percent decrease will counteract a higher percent increase because it's that sort of 6/5 over 5/6 kind of thing. One's up by just a fifth, one's up by a fifth, and the other's down by just a sixth. Okay, questions about that stuff? So with that in mind, since we know she's 16% faster, or she's 20% faster, she's taking 16.66% less time, that was my point, then we can answer the question. We do not need both together because we weren't asked how long she was going to take. If I needed to know how long she would reduce it by, then yes, it would change. If she were going 40 miles, she would save herself 8 minutes. If she were going 80 miles, she'd save herself 16 minutes, et cetera, right? It would depend on the length, of course. If you're driving across country, you're going to save a lot more than 8 minutes by going 10 miles an hour faster. But it's also important to recognize that that marginal increase goes down and down and down and down. And this is another really broad principle that you can use on the GMAT, which is that a fixed difference will matter less and less percent-wise as the numbers go up, right? Think about age differences. When you're little, your older brother or sister seems so old, and maybe they still do, but not as much, right? Like my brother's 5 years older than me. So when I was 1 and he was 6, or I was 3 and he was 8, that was a really big difference. Now that I'm pushing, I'm a little under 50, he's a little over 50, and we're both basically 50, it's just not that big of a thing. And you'll see that with percent differences, for age differences, for salary differences, for speed differences, right? So you see these people who are trying to go as fast as possible down the freeway because they're in a hurry. I get it, but your time reduction as the faster you go becomes less and less and less. So is it worth it for me to risk both, lives and speeding tickets and all else? Is it worth me to take all those risks to shave off less and less time every time I go up another 10 miles an hour, right? I get to the point where, okay, I've saved 40 seconds, right? But I was having to drive really crazily to do that, right? So as you go up, you get less and less of that return. Okay, questions on that? Okay, so let's run some other variations on rate and time. So you don't have to do see how long this takes you. We'll just give you a minute to try some of these. I want you to think about if you're a runner. I don't know. I was asking earlier if anyone's a runner, so let me know if you are. I'm a treadmill guy. I like to go to Orange Theory or to the local gym and see if I can go fast on the treadmill. I was never super fast on the street. So I'm often thinking about, how fast I'd have to go to hit a certain mile time, or what mile time I'd get if I went at a certain speed. Lovely thing about a treadmill is you can control it. Makes it very good for GMAT word problems, right? So what I want to think about is, okay, if I want to run, say, a 10-minute mile, or a 6-minute mile, or yikes, a 4-minute mile, right? I know there's some people who've run a little faster. I'm not going to be one of those. How fast do you have to go in miles per hour? So take just a moment to look these over, try to calculate some of them, and see if you could cheat a little bit. In other words, if you know some of these, you're going to know some others, and you shouldn't do 6 totally fresh calculations. And that'll come up a lot when you're dealing with something that has a lot of data, like an IR question or a comparative question where you're maybe looking at a before or after different cases, or you're testing a lot of situations. You don't want to do all the work. Okay, so take a moment to calculate a few of these. Okay, so let's try to grab some of this stuff. So 10-minute mile. How fast do I have to go to run a 10-minute mile in miles per hour? And how do I figure that out? A few ways I could do it. Curious what people tried. I could simply make a sort of a table. I could say, hey, 10 minutes would be 1 mile, or maybe I'll write it the other way, 1 mile in 10 minutes. So that's 2 miles in 20 minutes. And at some point I can sort of see which way the wind's blowing and say, all right, so that means that's going to be 6 miles in 60 minutes. That's going to be then 6 miles per hour. So then I could use that to generate a lot of these other ones, or I could do it directly, right? At some point I might say, oh, well, let's see. Then if a 10-minute mile is going to take 6 miles per hour, I think a 5-minute mile, I should have to run twice as fast because I want to take half as long. And I could verify that a couple ways. I could say, okay, 1 mile in 5 minutes means 2 miles in 10 minutes. And again, I could just multiply by 6 and say, oh yeah, that's 12 miles in 60 minutes. I could also realize that I can just divide 60 by these numbers, right? If there's 60 minutes in an hour, I could say, hey, 5 minutes per mile. You can use unit conversions. For those of you with a science background, you were probably drilled to death on setting up and canceling your units. So if I've got minutes per mile, and then I know I've got 60 hours per minute. Let me say that better. I've got I want to do the other way around, right? I'd want to say, well, I'm going for, sorry. Yeah, I'm doing 5 minutes per 1 mile. And I want to do 60 minutes per hour, right? So if I do that, it's going to look like I am canceling those out. But if instead I say a minute is a 60th of an hour, right? Then I can get that 12. Okay. So one way or the other, then I could say, all right, this is going to go in, and I can just divide that 60 by that 5, right? Another way to think about that is that I'm right. If I do a 5-minute mile, I'm doing 1/5 of a mile per minute. And then it's easier to cancel that 60 minutes with that 1 hour. So getting things in a similar term, like this was kind of weird to look at, and I don't quite know what I have, and I end up squaring them in minutes. Whereas here I can say, oh, if I could set this up so these cancel, I know I have something that means something to me. And then I'm going to get 12 miles per hour. Okay. And then all the rest work out proportionally. I could divide by 60, right? Some of these come out a little funny, right? So 8 into 60 doesn't work out that nice. But if I say, hey, 60/8 is 30/4 is 15 halves, what I'm trying to do is avoid anything where I have to get really calculation heavy, long division calculators, because I don't have any of that on the GMAT. So I want to be able to say, for instance, to divide by 8, to chop it in half, chop it in half, chop it in half. So 7.5 miles per hour. And then I would know from there that to do 7.5, I would need to go 8 miles per hour. But I could also do these proportionally. I could say that this is that 8-minute mile is 8/10 as long. So I need to go 10/8 as fast, right? 10/8 is 5/4 times 6, right? And then I would get 7.5. And so I could do this kind of thing. Similarly, with a 6-minute mile, it's 3/4 as long as an 8-minute mile. So I need to go 4/3 as fast. 75 is like 3/25, 3/4. So I could then say, hey, this is 10 miles an hour. Or of course I could do 10 times 6 is 60. And then the dreaded 4-minute mile, I can just divide 60 by 4, and I'm saying I'm going 15 miles per hour. But notice that as I want to shave a minute off, not only does it get harder and harder to do physically. I don't know how many of us are going to run a 4-minute mile, but the corollary of what we saw before, that a given fixed increase in speed drops your time by less and less, is illustrated here, that if you want to drop your time by the same amount, you have a larger increase in speed. So to drop my time from 6 minutes to 5 minutes by just 1 minute, I have to increase by 2 miles an hour. To drop it the next minute, I have to increase by 3 miles an hour. If, heaven forbid, I was going to try to run a 3-minute mile, good luck, I would need to go up to 20 miles an hour. I'd have to go up by 5 miles per hour. And you can see it as a percent, it becomes increasingly larger. I'm going up 20%. I'm going up 25%. Going up to 20 would be a 33.3% increase. So my percent increase in speed gets larger and larger. In some ways, this is kind of like what it feels like when you're trying to get that 700 plus score. It was maybe not so hard to increase from a low point to an okay point, or from an okay point to a better point. But as you're trying to get from an excellent score to a really excellent score, it feels like trying to run that 4-minute mile sometimes. I think more of you are probably going to knock out that 700 plus than are going to run Olympic speed mile times or anything like that. But hey, maybe you're one of those powerhouses that does both of those things. Awesome for you. Okay, questions on any of this before we move forward? So this is the kind of stuff, I mean, I'm going to be honest, this is the kind of stuff that's going through my head all day long. And if I'm exercising, this is what I'm doing. So I'm partly just trying to invite you to find this for a lot of other things. And what you can see, we're not going to do this in depth, but if you're watching this recording, you could pause this and try some of these just to see what happens. If you know that the minute per mile, like miles per hour, and the number of minutes per mile, multiply together to make that 60, right? 4 times 15 is 60. Then you could quickly say, all right, so if I go up to 5 miles an hour from 4, before I was running a 15-minute mile, now let's see 5 times what? Well, we've already seen 5 times 12. So this would be a 12-minute mile. Some of these get a little ugly though, because I don't know exactly what 7 does into 60. I know it's somewhere like 7 times 9 is 63, so it's less than 9. So it's a bit under 9 minutes. But another way I can see this is here, I'm going 5/4 as fast. So I take 4/5 as long. And 4/5 of 15 is 4 times 3 is 12. Here, I'm going 7/6 as fast. So I go 6/7 as long. And so I take off a seventh. A seventh of 10 is going to be more than a minute, right? Because a seventh of 7 would be a minute. A seventh of 10 is going to be, well, 10 sevenths minutes, about 1.5 minutes. So it's really closer to 8.5, right? And so I could keep going with this. 9 is, again, 9 times 7 is 63. So this will be less than 7. But it's also going to be, you could say, 8/9 of 7.5 if you want to find that. So some of these are ugly, some of them are not. This will be 10/11ths of 6. So now we're saying, I'm just going to take an 11th off of 6 minutes. I'm definitely not reducing that by a full minute, right? Definitely not reducing it by a full minute. It's going to still be 5 point something. And as you go up and up and up, it's the same thing. If you're already running a 5-minute mile and you get a mile an hour faster, you're only reducing your time by 1/13. So that would be 1/13 of 5 minutes, right? So 5/13 is less than 30 seconds, right? It's in between. If you say figure 5/15 is 20 seconds, it's a third. It's gonna be in between 20 and 30 seconds. Okay. All right. I saw a question about individual planning and stuff like that. Happy to talk for a minute after the course if that works. Okay, cool. So these are just some kinds of things you can do. But if you got nothing else out of this particular part, then these two things, I would still be happy. And those two big things to me are these. One, rate and time are reciprocal, right? If I go, 5/3 as fast, I take 3/5 as long. Two, and then we'll apply this to another problem. A fixed increase or decrease or difference, like an age difference, matters much more percent-wise when the values you're working with are small than when they are large, right? Man, when I wasn't making very much, when I was making minimum wage and I got, $1 or $2 raise per hour, that was a big deal because it was a large percent of my income. Now it's nice. I'm sure no one is sad about getting $2 more an hour or anything like that, or getting certain number of thousands more a year or whatever cool raises you're getting. But the more you're making, the less it matters. If you're a billionaire and you get an extra $1,000, you don't really notice. Okay. So those are two principles that show up over and over again, and you might be amazed how often you can use these on the GMAT and in life. I want these to show up on the GMAT. Not that I don't care about your life, but we're here for the GMAT. But if you start noticing these things in your life, then they're much more likely to be something you think about when you're dealing with the GMAT. One other principle we could add here is that if A is 20% bigger, or in general, like if something is X% bigger, then the other thing is not X% smaller, right? And so to put that, more clearly, if I have, say, a 20% increase, that's going to be offset by just a 16.66% decrease. If I have a 25% increase, or if I am 25% taller than my daughter, I don't think I am anymore, then she is 20% shorter than me, right? And you can see these by plugging in numbers, right? So imagine that she was 4 feet tall and I was 5 feet tall. We're taller than that, but okay. Well then, okay, the 25% is 1/4. But for her, compared to me, it's compared to my height. So then it would be 20%. And in general, you'll see these kind of differences because the percent down is of a larger number. And so it'll be a smaller percent. And that shows up all the time. And a lot of people don't think about those directions, or they do, but then they get turned around. And so it's a quick way to knock some things out. A lot of times on a problem solving, for instance, you can knock out a few answers just saying, well, I don't know what the exact percent decrease is, but it's not that number. It's not equal. And in fact, it's less. Okay. So let's look at this. Hope no one's too shaken by a discussion of income inequality, right? Look, here's people making a lot of different pay rates, right? And we don't have to have any given opinion about whether we should give them raises or anything like that. But if we are going to have opinions, we ought to get our math right. And I think that's really important. So if you look at these people who are making $10, $20, 40, 50, or 100 an hour, we want to think about the percent pay increase that it'll represent for each person. And using the principles we already had, we already kind of know one thing. It's going to matter most of the people making the least. And that fits our common everyday understanding of things, right? If you're making $10 an hour, you're much more excited to get a $5 raise than someone who's making $100 an hour, right? So we could sit there and express it, right? So we could say, hey, 5 over 10 would be a 50% raise. 5 over 20, well, it's got twice the denominator, so it'll be half the amount. Now we're doubling that again, twice the denominator, half that amount, right? So we're only going up by 1/8. Here I got 5 over 50. Here, instead of adjusting from the others, I just know what 5 over 50 is. And then we got twice the denominator, half the amount. So use those things to your advantage. But it's also, I think you know that 5 over 100 is 5%. So one thing that's really important to notice is that the person at the bottom is getting a 50% raise and the person at the top is getting a 5% raise. Depending on who you are in this scheme, you might, or what your views are on such things, you might have different views about what that means. For instance, one person might say, hey, it's not fair. The people at the low end of the tier are getting a much better raise than the people at the top in terms of percent, right? If you heard that everyone was getting a 50% raise, but you're one of the higher earners, you might be disappointed that you're only getting a 5, 10, 12% raise, right? On the other hand, if someone said, hey, if everyone makes $5 an hour more, prices will all just go up equivalently. Well, that's tricky. What percent of people are at each of these levels, right? If almost everyone's making $10 an hour in the country or in the world, then yeah, when wages go up to 15, then people are making 50% more overall, and maybe prices would just go up 50%. But if the idea is to level things more, then you might say, well, wait a second. What if a lot of people are up here? Maybe prices would only go up by this much for that, not for them, but like maybe not everyone's spending power is going up by 50%. So maybe not all prices are going to drive up that easily. Not trying to become an economist or politician here, but it's trying to think about how we look at that math when we're doing these. And this kind of trick, again, shows up over and over and over again in GMAT questions, where you're trying to say, hey, it really does matter, especially if it's data sufficiency and you don't know if you know the numbers. It really does matter. I think we all know already that $5 is a different percent of different numbers. That hopefully was not a revelation, but it's recognizing how that shifts over time. So then, the GMAT might ask a very formula type question, right? So what if they said something like, the top earner at a company makes 85,000. And the bottom earner makes 10,000. Okay. So then using the same idea of 5 for a second, what if I said if X represents the ratio of top to bottom earners' salaries, by how much will X decrease if each worker gets a $5,000 raise, right? So this is a more GMAT-like question than what we just did, right? So I've got someone making 85, they're at the top. I've got someone making 10, they're at the bottom. They're each going to get a $5,000 raise, so is everyone else. And we're looking at some kind of measure of like a ratio, an income ratio. Some companies have this kind of thing of like the top earner will only make this many times what the bottom earner makes or something like that. So maybe they're trying to track that. So I wanted to think about what happens to that measure X? If X always represents that ratio, normally we think of variables as staying put, right? I calculate what X is and that's that. But if X is a measure that they use, say, quarter after quarter, to say, what is that ratio? By how much does it decrease? Try this out, chat it in if you get it. How much would that decrease? I'll start putting up some of this work, right? So we have I'm a big booster of before and after charts. And so I can just kind of track some of the stuff in here. Say, all right, if X is the ratio of top to bottom earner salaries, I'm not going to end up expressing it as a fraction necessarily. I could do 85 to 10. But if I'm going to subtract, I might just want to get this as decimal. So I'll call this 8.5. And hey, let's see, 30 goes into 90 3 times. So 15 goes into 30 twice. That'll be 6. So you can break that into pieces. If you wanted, you could also do something like 90 15ths and take out a 5, 18 thirds equals 6. If you don't already know the 5's trick, I use that. I can't even tell you how often, just all the time. 5's trick is just to divide by 10, you knock a 0 off. So to divide by 5, you do that and double it. So if a 10th of 90 is 9, a 5th of 90 is 18. And I probably use that every day at some point or another. And so that difference in X will just be 8.5 minus 6 is 2.5. And so the idea is, and again, this is why people disagree so much about, pay raises for folks on the bottom end of the row, is clearly that measure, if you think of it as a ratio of inequality of earnings or just differential in earnings, right? That ratio shrinks when everyone gets a raise. So the person at the bottom is catching up with the person at the top. And depending on how you feel about that, you might have differences of opinion about whether we should do this, right? But that's what's happening. It's not simply because $5 matters more to people at the bottom than the top. It's not going to stay fixed, this ratio. It's going to, if we add fixed amounts, it's going to keep decreasing. And that's another general principle you can have. So another general principle that shows up all the time is if I increase the top and bottom of a fraction by the same amount, the fraction gets closer to 0. To 1, I'm sorry. So depending on whether the fraction is less or more than 1, that means it either goes up or goes down, right? So think about being outnumbered, right? We're playing tug of war and it's 3 to 2. Well, unless those 2 are pretty strong, they may well be going down. But as we, that's, 1.5, right? As we add people to each team, maybe now it's 21 to 20. We've added 18 to each team. Now, what is 21 divided by 20? Well, let's see, 21 divided by 10 is 2.1. So this is 1.05. We were only outnumbering them by 1/20th, which is 5%. And imagine now that it's, 1,000,001. It's a big tug of war game. To 1,000,000, it's basically 1. Sure, it's not exactly 1. It's slightly more than 1, but that outnumbering doesn't really matter. It's going to matter much more how strong the people are on both sides and how much they weigh than there's one more person. And this is true for all kinds of things. This is why when you're playing a chess match, if you're losing, you don't want to trade a lot of pieces because that advantage actually grows. If you have one more piece than me, but we're just starting, that's bad for me, but it's not a big deal. If you have one more piece than me and I don't have very many pieces, I probably can't win. And so we're always looking at those kinds of ratios. Okay. Questions on that? We can also connect a lot of this stuff to the idea of weighted averages, right? So think about any kind of thing where I'm trying to hit a goal. This could be, you know, for those who like the treadmill thing, it could be running on the treadmill. For those who are just trying to make some money, it could be about making money, right? So let's say that, you know, my target here is save $1,000 a month. Okay. And let's say I have 5 months where I just save 800. And I have 26 months where I save 1,000. And I have 6 months at 1,200. Do I hit my target? What do you think? If I try to calculate this weighted average, saying weighted average might put people off because you might think, oh my gosh, I'm supposed to add up 800 times 5 and 1,000 times 26. Okay, it's 26,000, and 6 times, you know, it's 7,200. And divide by, what is that, 37 months? No, in fact, all the ones where I actually hit the average, I can ignore, because for those months, I am at the average. It's like if you want to be average and you get a B, it doesn't change anything, right? Or let me put it this way. Yeah, sure. If you have bad, you know, below B grades, then it does. If my grade point average is a C and I get a B, that helps me, right? But if I already have a B average and I get another B, nothing changes. If I'm saving $1,000 a month and I save another 1,000, I get more money, but my average savings doesn't change at all. If I'm hitting the average doesn't change. So all I really need to look at is the over under. And you'll notice that these are each under by 200, and these are each over by 200. But I have more over than under, so I'm over my target. And I do not need to calculate. It won't be drastically over. I have 1 extra month where I save, you know, an extra $200. So I'm pretty close to my target over these months. But if they changed the number of months at 1,000, it wouldn't change the answer. And as long as this number is more than that number, then it'll still mean that I'm over my target. If they balance out, if I have 5 months at 800 and 5 months at 1,200, it would match out exactly. So the same thing could happen if you're running, right? If I want to, let's say I want to run 3 miles in 20 minutes. All right. So I could say that's 9 miles an hour. Well, what if I run 8 miles per hour for the first 5 minutes? Okay, so I'm under my target. Let's see. Then I run 9 miles an hour for the next 10 minutes. Well, that changes my average in the sense of it's up from 8 miles an hour, but 9 miles an hour is the target. So I'm hitting the target. So you could think of those as I'm doing what I'm supposed to do. It's like when you're doing a GMAT section and you're actually spending 2 minutes of problem. You're not necessarily getting ahead, but you're staying at the target, 2 minutes of problem for quant. So what do I need to do for the next 5 minutes? I need to run 10 miles an hour for the next 5 minutes. And those balance out because the 8 and 10 average to 9. So when and this is a general principle with rates, that when you work for the same amount of time, you can average the rates. It would be different if I said I run the first mile at 8 miles an hour. I run the second mile at 9 miles an hour. That would be a different thing. Because if I do that, I can't just make up for that by running that 10 mile an hour. And we saw why, right? Because when I run 1 mile an hour faster, the difference in time shrinks every time I go up the chain. And so the loss I had from running a 1 mile an hour too slow needs to be offset by more than one on the other side. So I may not want to calculate it, but I can know I need to run more than 10 miles an hour for the third mile to hit my goal. And that's the idea of weighted averages. Okay. For those of you who are getting exhausted just thinking about all these rates, let's do one other thing, which is Fahrenheit Celsius calculation. I've seen this get tested directly on the GMAT, so I'm going to give you a GMAT-like question to try. A lot of people tell me, hey, I don't ever do this in real life because I have a phone for this and I don't need to calculate these things, even if I'm going from Fahrenheit countries to Celsius countries. But on the GMAT, or if I'm from one of those countries and living in the other, as many of my students are, but for the GMAT, they'll ask in a ways where maybe recognizing what I'm able to do with the formula will save me some time and some trouble, make things a little easier. So try this one out. I'm going to give you a poll again. Pull this one in when you think you got it. Also see if you can get rid of some answers that don't make sense. Okay, if you're watching this on video and you're finding you still don't have an answer, you've got some company. I'm not seeing a lot of answers here. Let's see if we can find some ways to narrow this down. I may not know much about Fahrenheit and Celsius, but I've got this formula they've given me. And I've even seen, I believe like I've seen a question where they use this exact formula and they never mention temperature. So like, oh, by the way, there's this thing you can do where you multiply by 5/9 and when you take it, and they don't mention, whoa, that's the formula for temperature conversion, but here it is. If I go up by 180 degrees Fahrenheit, should that be more or less in Celsius? Because I'm taking the Fahrenheit and reducing it by 32 and taking 5/9, I should want to see something less than 180, right? Which is the Fahrenheit increase. Now, maybe what I could have put in were some answers over 180, because we definitely want to cross out those as well when you're converting from Fahrenheit to Celsius, you will go down. But the GMAT's not always that nice. They don't always give us a lot of bad answers, but sometimes they do. Sometimes I'll look at a question, I'll say there's really only one answer that makes a lot of sense at all if you just stop and consider what kind of number I want. And then you might say, do I want my answer to be more than half, less than half, close to 180, far from 180? That's something to think about. So one thing I could certainly do is just apply the formula. I could say, okay, 360 Fahrenheit is going to be in Celsius 5/9 of 360 minus 32. But I don't have a calculator. This is starting to look kind of ugly. But the answers, notice the answers are not approximations. It doesn't say approximately how many degrees. It says how many, which implies that somehow I'm supposed to get a clean answer out of this. So what should I do? Probably not try to find 5/9 of 360 minus 32 right now. Especially because I'm also supposed to find 5/9 of 180 minus 32. And when I have to find the same fraction or multiple of two numbers, I can undistribute that number, can't I? So I'm much better off saying, all right, before I take 5/9, let me pull that thing out and say, okay, well, I'll do the 360 minus 32. So 360 minus 30 is 330, so that's 328. And 180 minus 30 is 150, so that's going to be 148. Okay, that's a little better. And then I say, okay, well, what is that? That's 5/9 times, let's see, 328 minus 200 would be 128, but we're at 148, so that's 20 more. So the difference must be 20 less than that. So that's 180. In other words, I'm not quite taking away 200. I'm taking away 20 less than that. So interesting that this worked out to that difference of 180. Could I have seen that coming? Maybe you did. So then I could take 1/9 of 180, and this works out clean to exactly 100. So it's interesting that although I did all this work, not only could I save myself doing some calculations, the answer ended up just being 5/9 of 180. Why is it that the minus 32 didn't really end up playing much of a role? And Mike asked a really interesting question. How do you slow down enough to remember to acknowledge that? Which that were you talking about? Which part of it, Mike, were you saying I need to acknowledge? While you're talking about that, where I combine the two things to simplify. Yeah. Well, partly it's just saying, sometimes I turn my strengths into a put down a little bit. I'll say I'm lazy and entitled, right? Because it's partly true. And I want you to be a little lazy and entitled too on this test. If you just think of it as, okay, head down, I'm supposed to just be smart and work hard and do all this stuff, you might be doing tasks that aren't even possible, or that are possible, but not within a reasonable amount of time unless you are a calculation savant of some kind. Right? I am really good at the GMAT at this point in my life, right? But I don't look at 5/9 of 360 minus 32 and go, oh, I know what that is. I do not. And I wouldn't expect to, right? If you actually do the subtraction of 328 and try to take 1/9 of it, you're going to find that 9 does not go in, right? 9 goes into 270. It goes into, therefore, 315, which is 270 plus 45. It would then go into 324, but not into 328. You can tell also if you add the digits, 3 plus 2 plus 8 is 13. When you add the digits of a multiple of 9, you should get a multiple of 9. You should get a 9 or an 18, right? A little fun fact, right? So 360, you know, is a multiple of 9 because of the 36, but also because 3 plus 6 is 9. And any multiple of 9, the digits will add to a multiple of 9. So that's one way. I'm being a little bit entitled. I'm saying, hey, I don't want to work that hard. There's got to be something else I can do. But also notice that once I do that, I don't even have to do the subtractions because I could say, wait, I'm subtracting 32 from both of the things I want. So I might have even said, wait, once I kind of pull this 5/9 out, I might have said, hey, I'm taking 360 minus 32 and taking away 180 minus 32. Why am I taking away 32 at all? To me, that's like saying, who's taller, or how much taller am I than you if we both stand on the Eiffel Tower? Well, let's see, my height, okay, let me look up the height of the Eiffel Tower, and I'm about 6 feet, so 6 feet plus that, and then your height is, who cares about the Eiffel Tower if we're both standing on it at the same place, right? Then it doesn't matter. So I don't need the 32. And what this gets us is that the marginal change in temperature is only going to be about 5/9 of a degree Celsius for every degree Fahrenheit. Reciprocals, 9/5 going the other way. So if the temperature goes up from 20 degrees Celsius to 21, that's going up 9/5 of a degree Fahrenheit, which is what, 1.8. Okay, so going up 1 degree Celsius is closer to going up 2 degrees Fahrenheit, but we don't have to worry about that offset. The 32 just is because, to bring in the real world part of it, 32 is because in Fahrenheit, we have boiling at 212 and freezing at 32. And so the 32 is just to get the same beginning point. And then from there, you're getting, for every degree Fahrenheit, you're only getting 5/9 as far up the scale as for Celsius. With Celsius, it only takes a 100-degree increase to get from freeze to boil, whereas in Fahrenheit, it takes a 180-degree increase to get from freeze to boil. So the 32 is just saying, where do we start? But every time you go up 100 degrees Celsius, you're going up 180 degrees Fahrenheit. And that's the real shortcut for this question, right? So if I say, oh, plus 180 Fahrenheit is just going to be plus 100 Celsius, then that's it. That's all I have to recognize. And there's a reason that the problem asks you about that particular juncture. Not from 180 to 360. It could have been from 200 to 380. But the idea is, not only did it double, but it doubled by an amount 180 that corresponds to an increase of exactly 100 degrees Celsius. And that's another way to get there. So yeah, comment, it's easy to rush into calculating. Yeah, and I think the biggest mistake people make on the GMAT, like overall, well, maybe the biggest mistake is people study quant all the time and don't study verbal, and that's a huge mistake for most people. Most people should be spending about half their time on verbal. But other than that, probably the biggest mistake tactically people make is that they start going into things too soon. On verbal, that usually means they're not predicting an answer. They're not reading carefully enough. They're not identifying what the question is asking. On quant, they haven't rephrased the question. They haven't figured out what we're really dealing with. I'll talk to students who are so stressed by this test, and I get it. It's a stressful experience. It still is for me, and I have nothing to prove, but it's still stressful. You go into these questions and you're just like, oh, I got to be fast and smart, and I've got to get all this stuff. Right? Take a minute to take stock. What kind of question is this? What do I know about it? What do they really need to do? And then when I'm at a given stage of math, before I start solving, where's this going to go? And that's like anything. I think about, like getting physical things done, right? There's very efficient and inefficient ways to say load a moving van. Oh my gosh, I put all the heavy things in on the wrong, I saved all the heavy things for last. Now I'm trying to shove them in. Should I put them in first? Or what about here? I set them there, or went down that way or that stair. There's I'm yammering, but there's a lot of ways you can do things. And there's someone who's experienced, I'm clearly not an experienced mover, would have all these ideas about exactly how to do it. But the analogy I use all the time that I think we can all relate to is, if you're about to move, don't do any work that you're just going to have to undo. Don't build that bookshelf, put it up, put all your books on it. If next weekend you're moving and now you have to take all the books down and box them up, you have to disassemble the bookshelf, or at least cart it down the stairs in that bulky form, right? So don't do work you're about to undo. Here, we weren't going to undo the 5/9. We weren't going to multiply back by 9/5, although then we definitely would not want to calculate this. But I didn't need to do so much work. I didn't even need to do the 328 and 148, because an intermediate step might have been, hey, what's 5/9 of 360, double parentheses, 360 minus 32 minus 180 minus 32. And if I kind of run that out, those 32s are going to cancel, right? I'm going to have a plus 32. They're going to cancel each other out. So recognizing that. Okay. I'll stop there because I know we've run a little bit over. I hope these things were helpful to you. If you want to check out any of our future classes, would love to see you around. I also do these free pep hours on a pretty regular basis. If you would like to reach out to our team and let us know anything you'd like to see in a future free prep hour, I'd love to know what those things are. But you can also check out any of our classes, show up for session 1 once you've registered, and check it out for free to see what's going on. All right, everybody, best of luck with your test. Hope you found this helpful. Stick around if you have any questions or want to let me know anything. Other than that, have a great week. Take care.